We discussed earlier that embedded software is purpose-built software and it is shipped with the device. As you can imagine, there will be different software programs to control different functionality in that specific kind of device. When you change the temperature, the air conditioner tries to bring the room temperature to the new value as quickly as possible. To do so, it may increase the airflow initially until the room temperature is closer to the set point and then reduce the flow into a gentle breeze as it gets closer to the set point. In case of a digital camera, when you want to focus on a subject, you can press the shutter halfway and you will notice fine rotation of the motor that tries to adjust the lens to get the object in focus. In both these examples, you can identify three-step process. First is to read the current state and the desired state. Second step is to compute the difference or gap between these two states. And the third step is to execute the command so that the current state is as close as possible to the desired state. Once the system reaches the desired state, then it will be continuously monitored and maintained in the same state until there is a new desired state. With that, let's see what benefits we get with the embedded software. So far the discussion, you already have seen how useful an embedded software can be. It's almost impossible to imagine any modern system without an embedded computer. Firstly, embedded software makes a system very powerful and flexible. We can reduce the size, weight, and energy consumption of the system in general while increasing the safety and performance. Most products these days have the capability to update the software over the life of the product. This allows to add new functionalities, improve the performance, or even fix defect that was present earlier. This effectively increases the utility of the product and makes it usable over longer period. With embedded software offering so many benefits, it's no surprise that more and more systems are becoming software intensive. The presence of embedded software is becoming pervasive across products in all industries. When you start and drive away a modern car, there can be over 100 electronic control units controlling a variety of functions which you may not even realize. Similarly, there can be millions of lines of source code present in an aircraft controlling critical functions and helping it fly smoothly and safely. The story remains same, whether it is a medical equipment, industrial system, or consumer goods. Something that we haven't spoken specifically so far is how software can help improve the safety of the system. When you engage the lane keep assist function in your ADAS-enabled car, you trust the car to maintain the lane or warn you if the car sways out of the lane. With automated emergency braking feature, you trust that your car will automatically apply the brake to prevent the possible collision. Similarly, the airline pilot relies on the information presented to him over the cockpit displays. He trusts that the autopilot can safely fly the aircraft within its operating conditions. As you can imagine, these are a class of embedded systems that perform safety and mission-critical functions. The results can be catastrophic if these systems fail to deliver as expected. Developing embedded software for such critical functions is a very challenging and demanding task. We will talk more about these challenges and solutions later in the series. Now that we have an overview, let us quickly look into the typical process of embedded system development. Let us split the embedded system into hardware and software, then look into each with comparable steps. Whether it is hardware or software, the starting point is a document that outlines the requirements. The requirements specify what the product should do. It's very important to have the requirements that are correct, complete, unambiguous, and testable. The requirements must include functional, non-functional, performance, and safety attributes, among many others. Hardware design can include mechanical structures such as enclosures, cabinet, mounting, etc., which may be created by mechanical engineers using CAD tools. These CAD drawings are later used to create a physical prototype to ensure that the design is correctly realized. Later it moves into production with the production quality manufacturing process, where all the attributes including fit and finish, tolerance, etc. are controlled within acceptable limits. Designing a system is usually a multidisciplinary task. You will usually find mechanical, electrical, electromechanical, electrochemical, electronics, optical, electro-optical, thermal, software, and possibly many more disciplines coming together, requiring each topic to be addressed by subject matter experts following their unique development process, tools, and artifacts. Now, coming to the software development, we can conceptually extend the same process and explain each step. As we did before, we start with requirements once again. This time, we focus on requirements allocated to software, as we do not concern ourselves with other areas of system development. With that, we perform a high-level design, which is software architecture. A software architecture is very similar to the blueprint of a building in the sense that it depicts how the software components are going to be designed and integrated. In the next step, we translate this high-level design into low-level design and start with the implementation. Implementation is the process where we produce source code, which are nothing but a set of instructions to the computer in a language such as C. Next step is to bring all these source code together, interface with hardware, and compile them into an executable, which is the deliverable as far as the software is concerned. This must be tested thoroughly based on the requirements to ensure that all required functionalities are correctly and completely implemented while meeting the required performance and other criteria. Now that we have looked at the embedded software development process, let us look into the aspects that need to be concerned while developing high-quality embedded software. Embedded software is built to run specifically on a given hardware, as we discussed earlier. This means the embedded software developer must concern not only software development, but also be aware of the hardware. The engineer should be aware of electronic circuit, peripheral devices on microcontroller, as well as the circuit board. He must also be aware of hardware-based debugging techniques to fully understand and fix issues arising out of complex interfacing between hardware and software. Most embedded applications can be complex enough to require an underlying operating system. These operating systems are conceptually similar to a desktop operating system such as Windows, but designed to meet the constraints of an embedded environment and deliver real-time performance. An embedded software developer typically needs to be aware of the usage of real-time operating systems, how to schedule an application, how to communicate with peripheral, and how to manage interrupts, etc. Software optimization is another important consideration in case of an embedded system. Due to cost implications, hardware performance and memory availability is always constrained. Many devices could be operated on low power due to portability or limitations of thermal dissipation. Embedded software must meet the constraints such as timing, memory requirements, power consumption, etc., and exploit the hardware capability to deliver the best possible performance. Most embedded software performs autonomously with little to no human interference, which means the software must be developed to high standards. In case of desktop applications, a software defect could be a nuisance. It might force you to restart the application, or sometimes even the operating system could crash. Such defects hardly cause any safety issues. However, we cannot tolerate a safety-critical software in an aircraft causing a similar shutdown. Therefore, it is obvious that we follow best practices while developing safety-critical systems and comply with industry standards. These standards have evolved over several years and provide guidance and objectives to meet so that the software can be good enough to be deployed in such critical systems. In case of high criticality applications, the constraints can be so stringent that complying with these standards could add up to an extra 4 times cost and efforts compared to the baseline. With increasing software in systems, security has become another very important topic. While safety deals with the issues arising out of the malfunctions in the system, security deals with the external intrusion. You can only imagine what someone can do if they manage to get a remote, unauthorized access to critical functions of a car or an aircraft. If the system is not secure, safety becomes an illusion. We have seen so far that developing an embedded software, especially the one that must meet safety and security necessary for high critical applications, is not only extremely challenging but also highly expensive. Industry is always on the lookout for solutions that can help them develop these complex applications easier, faster, at a reduced cost, while still complying with the highest levels of industry standards. Ansys SCADE software is a model-based development and qualifiable code generation environment based on formal semantics. With a rich experience of over 2 decades in multiple safety-critical industries such as aerospace and defense, rail, nuclear, automotive, and industrial applications, Ansys SCADE offers safe and secure embedded software development capability that meets your performance constraints and fully complies with the most stringent standards out there in the industry. While doing that, SCADE also delivers around 50% savings in terms of cost and efforts while speeding up the certification time as attested by our global customers. Visit back this page for more videos on SCADE software. In the meantime, you can learn more about SCADE software here. Thank you for your time and interest. Until next time.